I have here footage of 4 separate collisions. Using Tracker, a video analysis program, I'll use each one to demonstrate a different collision-based concept. Collision 1, Symmetry. While the transfer of momentum in this collision may seem unintuitive, if we consider the perspective of an observer moving at half the initial velocity, adjusting the framing and removing the backing video, we see that the interaction is, in this frame of reference, symmetrical. Approaching this idea mathematically, imagining a puck moving right with a velocity of 10 towards a stationary identical puck, post-collision the first stops and the second moves right with a velocity of 10. For an observer moving at half the initial velocity, all the velocities are increased by 5 towards the left, causing each of the initial and final velocities to be equal and opposite, or in other words, symmetrical. Collision 2, right angles. In an elastic collision, kinetic energy is conserved, meaning that the initial kinetic energy equals the sum of the final kinetic energies. If the masses are the same, we can divide out half m, giving the velocities in the form of the Pythagoras equation, an equation specifically for right-angled triangles, proving that there must always be a right angle between the final velocities of equal masses colliding elastically, as we observe here. Collision 3, momentum conservation. Because there are no unbalanced external forces, we can assume that momentum is conserved, meaning that the difference between the initial and final momentums should be 0. Using the tracker data to calculate the difference, we get a difference of 0.76%, small enough to dismiss as random error. Collision 4, center of mass. Another way of phrasing momentum conservation is to say that the velocity of the system's center of mass remains constant. Using Tracker to plot this, we indeed observe the center of mass marked in green following a near constant trajectory.